example of the bicycle. No matter how much in the classroom, if you know how to ride the bicycle, unless you get onto the bicycle, fall couple of times, injure your knees, put bandage on the knees, you are not going to learn how to balance it. So same is the swimming. Till the time you drink 3 4 liters of water, you will not be able to swim, no matter how good the coach is and how perfectly he will create a video how to swim. Unless you do it, you will not be able to do it. So practice is the only way. Is the CR of A section there? Who is the CR of A section? Okay, CR of B section. Any CR? So CSE and IT. Come in the chat window. CR, CRs of CSC and IT. Come in the chat window. Give your name and tell the section. This is the problem. And the CR of D. Good afternoon. Okay. Janvi, CRs of CSCD. Does it mean that only one CR of all the sections are there? Only one? What about A, B, C, E, F, G, IT, A and B? Now, Janvi, have you distributed the recording of all my classes? Excel sheet? No, no. The recording of all my classes. Which Excel sheet are you talking about? Janvi? On Google Drive, we are sharing the recording of my class. You mean the Excel sheet has got the recording of my class? Am I right, Janvi? And you are given it to your class. And regularly, as and when the class over, I think within 10 minutes, the link is uploaded from KMID side. So I hope without any delay, you are distributing it in your class. Janvi? Right. So the D section student have got no reason to say that we are not able to revise what has been taught in the class. Right. Similarly, I don't know that whether they are worth calling CRs if they are not even attending the classes. So I will request the faculties to remove them from their CR position and appoint somebody else who is effective. Right. So now, if the CRs are not distributing it, some complaint has come to me saying that we are not getting the recording and we are not able to revise, and that's why our performance is bad. But the case is that we from KMIT side are giving you whatever is required for the students. And the students, if you are not chasing your CR is in your interest. It is not in our interest. The steps are very clear. I teach. The record link is put up, and the CRs are supposed to distribute in the class. If the CR doesn't do the job, you can't sit tight on your at home and say, "Sir, CR did not give, so I was not having." What goes wrong if you call CR and ask he or she to distribute in the class? That much of initiative is expected from you. Anyway, data structure is one of the very important topics, and if you are aspiring to be in the dream company, the full knowledge of data structure is very essential. Now, my appeal to all the faculty members from ABC, EFG, and IT. Hello. Yes. Yeah. Okay. So now I'll request all the faculty members to please distribute this recording links to the CRs, and please counter check from the CR. Okay. So where we stopped is the BSc in order. Now in the BSc in order, as you see the code on the screen, it does not return anything, and you can see a recursion taking place as shown in the code. So the parameter required is the root, and based on the parameter, it's going to go in the in order. Now the in order fashion, as you know, is left root right, left root right. So as for that left, it goes to the root, then to the right. So this left subtree is over. Then again it goes to the root, that is 1, and then it comes to the right, that is 3. So in this order it should go. So if you consider the case 1, when you consider the case 1 when there are no nodes in the tree in the BST, then what's going to happen? It's going to check root not equal to null, right? Root not equal to null, false. And when there are no nodes, we have kept the flag is equal to 0. So we display that the tree is empty. So we move the case 2. Now case 2 is what? There's only one node. There's only one node. And of course, since there is one node, the left subtree and the right subtree both are null. Both are nulls. So this is the state. Now the base address of the root is 1000. So we are passing the root address as 1000, right? So root is not null true because it is 1000, which is not null. It gets into the if condition, it gets into the if bracket, and in the bracket there is a recursion. That is, the in order function is called, but called by changing the root address. Root address is changed to root of left. Now root of left is what? Thousands left is null, right? So again the same function call is given, but only change is that this parameter from 1000 has got changed to null, right? If not null is false. Flag equal to is also false because there is flag becomes 1 because there is one node, right? So it's simply going to return from to where it was called. Where was it called? It was called here. It was called here. So this goes return, does not return because there is return type is void, and goes to the next step. And what does the next step do? Root printf root of key, root of key is 6, so 6 gets printed, right? Then it comes to the next step, it gives a recursive call, root of right. Now root of right is null, root of right is null. So recursively, this null is passed as the address, null is passed as the address, and then again this condition fails. Again it comes back to the same call, it comes back to the same call, and because there is no code after this in the if condition, it's going to go back to where it was called. And this method will be called from the main function, so it will go back to the main function. So this is my case 2. Case 1 was when there were no nodes. Case 2 is when there is one node. Now let's see the case 3. Now case 3, we have the root node, we have the left node at address 500, and we have the sub node to the left node, and we have one more node that is to the right, right? So the left is also, there is not null, and right is also not null, okay? So presently we pass the root address, which happens to be 1000, and because it is not null, this is true, if condition is true. So recursively it's going to call what? The root of left, right? Recursively it's calling root of left. And what is the root of left? Root of left is going to be 500, right? So when the recursion happens, that is when it's called again, we are passing the base address as 500, right? Now since 500 is not null, this if condition is satisfied. So since the if condition is satisfied, it enters the if block, right? Again, we are calling root of left. Now we have already come to 500, and 500 is left, happens to be null. So when recursively you are giving a call, here you are passing null, right? When you are passing null, this is false, this is also false. So who has called this function? The function was called here, right? This function was called here. So simply, without returning anything, it comes to the next step, right? But what was the base address here? 500, right? So the root here is 500. So root's key is 4. It gets printed. So 4 gets printed over here. Then it moves on to the in order root of right. Right? It has not gone over here. Again, it has got a recursive call. So that recursive call has come, say, to this place. Now, what is the right of this? Right of this was 1500. So we are past 1500. So what's going to happen? Struct node 1500. 1500 not equal to null. True. 1500 not equal to null. True. So we enter the if block. Now in the if block, again we are calling the in order root of left. What is the root of left? Null, right? So the function again is recursively called with null value, right? Since it is null, this is false, so it's going to return where it was given a call, right? What was the base address here? 1500. What is printf? Root of key is going to be 5. So first we printed 4. It did not go to left because it was null, so it came to the right. Since the right is equal to 5, so it printed 5. Now again, in order root of right. What is in order root of right? So presently we are at base address 1500. 1500 is null. Null means what? It calls this particular function. Root, it returns nothing, so it comes over here, it returns. Now who has called? It has been called over here, right? So we from here, this step we came over here, so it goes back to the base address at 500, right? And it terminates. Who has called this function? This function was called over here, right? Then it comes and prints the right, right? Then it comes and prints the right. So 6 gets printed. So that is how in order traversal happens. First 4 is printed, then 5 is printed, then it goes to the root 6, and again similarly the right branch will happen. Similarly, the right branch will happen. So similar on this basis, we this function gets closed, this function gets closed, this function gets closed, and finally we come here. Okay, so that's what is a revision of what we have done in the previous class. I hope there are no doubts. In case there are any doubts, come to the chat window. In case there are any doubts, come to the chat window. Right. So one more function, that is insert. One more function, which is the last function, that the insert. With that, will complete the BST. Now this insert function, as you see the definition, it has a return type of struct node type. It takes two parameters: the node, which happens to be the root of that particular time, and and in addition to that, we also pass the key. In addition to that, we also pass the key. Just go through the code, and I will explain to you. Go through the code every step. Try to understand, particularly this side. Case 1, case 2, case 3. Yes, Kruti, anything you would like to say? Kruti, anything you would like to say? No? Okay, not an issue. Not an issue. Right. So, having gone through the code, we'll start with the case 1. Case 1 is what? There are no nodes. The first assumption is that there are no nodes. Means the tree is an empty tree. A tree is empty tree. So root obviously has to be null, but we would like to pass, we would like to create the key. We would like to create the root. We would like to create the root. So assume that we have passed the key as 6. Right? So node equal to null is true. Node equal to null is true. So if the tree is empty, now then we have to create the first node. Right? So if this is true, we are calling the new node function. So this is your new node function. I have discussed the new node function before also, but doesn't matter. I'll repeat it over here. Okay. Now, what is the item here? The item is nothing but the key, which we have passed it as 6, right? So 6 gets passed over here. Now struct node pointed temp, and we are dynamically allocating the memory, right? Then we are initializing the key value, and left and right we are initializing it to null and returning the base address of the temp, right? So the the structure is created first. Step 2, temp of key is equal to item, that's this item. So we are passing 6, so this is assigned. Temp of left is equal to temp of right is equal to null. So that's why this is null and this is null, right? And the base address is your 1000. Base address is your 1000. So when I say return temp, is going to return what? 1000 here, right? And since the return address, so it's going back to the main function. It goes back to the main function, and case 1, that is only node which is created, is added, and our root node of the binary search tree has started. Any doubt? so far. Oh, sorry. Thank you, Rohan. Thank you. Thanks for alerting me. I had by mistake shut down the mic. Are you able to listen to me now? Right. So now what we do, we pass four, we pass four, and the node address is 1000. Sure, sure. Okay, sure. Uh, right. Thank you. Yeah. Shankar, can you hear me now? Am I loud enough, Shankar? Jai Shankar? Or further loud? Right. Uh, right. So what we have done is we have passed the key as 4 and the node address is 1000. Okay. As you are seeing here, case 2, node key, node key is less than the root key. Root key is 6. So assume that the node key, so since we are passing the node which is say 1000 and this is key is 4, so this is not true. What? The node equal to null is not true. So it does not enter the if condition. That is, the empty tree condition does not does not stand to be true. So it comes over here. Key, what is the key? 4. 4 is less than 6. This key 4 is less than 6. Right? So what we do? What we do? Node of left. What is node of left? Thousands left is null. Right? But this is going to get replaced. What we have done? We have called a recursion. Right? We call a recursion. Now in the recursion, what has happened? Node of left. What is node of left? Thousands left, null. Right? So when the call is made, the node value is null and key is 4. Node value is null and key is 4. So when the recursion happens, this is null and this is 4. That's what I'm depicting over here. Right? At this step, this call was made. When the call was made, item is 4 and the node is equal to null. Are you getting my point? When this call was made, this is null and this is 4, right? So when it comes over here, this is true. So we create a new node. So that new node, assume this as 4, right? The key is 4. So we create a structure. Whose base address is 500. Left is null, right is null. That's what the priming happens over here. Temp of key becomes 4. So 4 gets assigned here. Left is null, right is null. Right? So at the present, if you freeze the code and the actions therein, then this and this so far is not connected. Right? The tree is not forming. This is isolated and this is isolated. Right? So when the call was made, this has happened, it returns. Returns where? It returns what? Struct node, right? Struct node base address. That is, we are returning temp. What is temp? 500. So this is going to get replaced with what? When the call was made, it went over here. This condition was satisfied. We came here. We called the new node function. New node was created. Key has been assigned 4. Left is null. Right is null. And last step, return temp. So this return is going to go where? Anybody? So sleep condition. Meghana Desai, node of left, question mark, question mark. What do you, how, Correct. Rohan, first if condition, this call was made over here. True? This call was made over here. So Rohan, you're right. First if condition, it has come here. But it is return. Return where? Return at this particular spot, because from here the recursive call was given. It went over here, it came inside, it called this function, it returned the 500 address, but this return is going to come here. Meghana Desai. That 3-4 questions you have put over there after left of node. Are you trying to ask me this question? How does it come to node of left? Are you understanding what I'm saying? Meghana? Not clear? Since you are not responding, let me explain. See, we are past 4 and the root is not null. So first it doesn't enter here. It comes here. 4 is less than node key. 4 is less than. Acha, you are answering, but you put question mark, so I got it out. Sir, my messages aren't going. Okay. I see. Okay. No issues. But doesn't matter. I'll explain it again for other students who, assuming that some of them have not understood, why this 500 gets assigned here. That's justification I'm giving. That justification I mean. See, first here the recursion has happened. It has gone there. The base address and the key. Now the base address happens to be null because what is the call? Node of left. What is node of left? Node of left is null, right? So this is true. So this is true. So if condition is true, we are entering over here flag plus plus. The second node is getting added key. So this function gets called. When this function gets called, the node is null, key is 4. A temporary structure is created in the heap whose base address happens to be say 500. Temp of key becomes 4. Left and right becomes null and return temp. Right? So this is going to be 500. This is going to get replaced with 500, but we are saying return. But when I came over here, I started from this particular call. So the 500 gets returned over here. When 500 gets returned here, this 500 gets assigned to node of right. Sorry, not here, here. This 500 gets assigned to node of left. Now this node of left going to get replaced with 500 like this. This node of left gets replaced with 500 like this. Jai Shankar, are you understanding? Since Meghna's messages are not going, Jai Shankar and Akash Deep, are you understanding? Jai Shankar, Akash Deep, Gayatri, anybody? Have you understood this insertion? Right. Okay, good. So even Meghna is able to respond. Fine. Now the case 2. The case 2. Now we want, suppose we are sending the key as 8. So base address is 1000 and key is 8. Key is 8. So obviously we have to come to the right side. Obviously we have to come to the right side. As per the BST, any key which is higher than the root key goes to the right. Okay. So 1000 is not null. 8 is not less than 6. Else if 8 is greater than node key, 8 is greater than 6, true. So node of right, that is thousands right, is equal to insert node of right and key. Insert node of right and key. This node of right is null. So this node of right is null. This key is 8. So a call goes over here. This is null and this is 8. Since it is null, since it is null, what happens? This if condition becomes true. So if the if condition becomes true, we are going to call new node key. We are going to call new node key. So that's what the new node key has been called, new node. By passing at the present, node value is null and key is 8. So again, a temporary node is created. Temporary node is created with the key as 8, left and right as null null, and the base address is 1000. It returns. It returns here. It returns. But where was the call made? The call was made here. So this address, this entire call is going to get replaced with the base address 2000. And that 2000 is going to get assigned to node of right. That is node of right. So this goes and changes to 2000 and it connects over here. It connects over here. So since recursively it is going to happen. Suppose we add 5. Suppose we add 5. So it's going to come here and to the right it's going to add. If we add 3, it's going to come over here and to the left it's going to add. Right? It's going to the left and it's going to add. So that's how recursively we are going to insert the nodes. Any doubts regarding the insertion of the left node and the right node, please come to the chat window and I'll clarify. Right. So looks like you are able to receive the whole idea, students, of conducting the exam, and there was a huge kind of representation. So don't conduct the exam, don't conduct the exam, this, that reason. The whole idea is that if you brush up what has been taught, the understanding of the higher level of difficulty chapters, right? Now the next chapter is going to be AVL. Unless you understand the binary search tree, how will you understand the AVL tree? Now to build your understanding, I have to ensure that you revise whatever has been taught, right? It cannot happen that the faculty will start teaching from any point of time the student joins and the student should understand. No faculty will be able to do that, right? So you as students also have the responsibility of brushing up what has been taught, and that's why that internal class test was kept, and unnecessarily you started trying to avoid it, and the result is in front of me, right? I'm not happy as far as the practicals or the coding is concerned. Now let me warn you guys. Today you may think that why should I focus on, I'm just in the second year, let me go to the third year, second semester, that time I'll start coding. It cannot happen like that. At least in KMIT, our record of placements is good only because we focus on students' understanding level right from the semester 1. You cannot come to semester 3 too and say, sir, I don't know C, so I'll open the book and start learning what is C. It cannot happen. You are unnecessarily wasting your time. Then you come over there and say, sir, the college is not doing anything and I'm not able to get placed. What is the use of joining KMIT? This and that. Please try to understand. You have to revise. You have to revise. You have to practice. You have to write the code. You have to, there will be errors. Understand what could be the error and fix the errors. Anyway, now the main function, we are displaying the menu as per the syllabus. Insert a key, delete the key, search the key, and display the key, right? So these are all the four things which are there in this code. And as per the case one, it enters the insert function which you have just now done. If it is the two, right, then we have already learned the delete function. That function gets called. If it is three, right, then you are expected to give the key which you want to search, and the searching will happen in the in order fashion. Searching will happen, and then the display is going to be in the in order fashion, right? So I will try and demonstrate to you. I think, yeah, this is the code. Yeah, the code got compiled, and we run it. And now let us see that the press, please enter the choice. Now there are no nodes because in front of you only we have started, and actually we should have been starting from 1. But say search 3 and enter. Search key, say 33. I enter. Oh, there is some problem. Let me see what is the, should not happen. So let me start from 1. The enter the key. I'm entering the key as say 6. Do you want to continue? So I say yes. Now search, say 3. Enter the key, say 6. So at so and so root address, I found the key 6. Again, I press 1. Again, I would like to insert a node. I say 1. Asking me the choice, I say 4. The key node has been inserted. Then do you want to continue? I say yes. And enter your choice. Display the binary search tree, say 4. So 4 and 6. Now this in order function always is going to show you in the ascending order. First the left, root, right, that concept. Okay. Again, I say 1. Again, I want to insert, say 1. I say 5. Do you want to continue? 1 for yes. Yes. Again, you would like to display, that is option number 4, to display the binary tree. Now, because 5 has been inserted, 4, 5, 6 should be the display. So when I say 4, so like that. Now let's go to, do you want to continue? Say 1. Now I would like to insert on the right hand side. So I give the choice as say 1. Enter the key, say 8, which is the root is at 6. So we are inserting 8. So it has to obviously go to the right. Do you want to continue? Yes. Now let us display. Display is what? Let's do searching also. Say 3. Now in the search, asking the key, I give 8, and he's saying key 8 found. Key 8 found. Now what you are seeing are the root address and the address at which the key is located, right? So we are displaying the address locations also. Again, I say, do you want to continue 1? I say yes. Right? Enter the choice. Again, I would like to say search, say 3, and let me give some 55, which is not there, and the key should not be found. Uh, there appears to be some violation error. Mm, enter the key 1. Do you want to continue 1, 2, uh, then it's 3. No, I'm not happy with the demonstration. So I'll try and do the demonstration probably in the next class or send you the code which works. It's not working, so there should be some error in somewhere. Okay, so uh, yeah, so the demonstration, maybe the file which I'm using is not correct file. Let me see. I'll once again give the demonstration. I'm not satisfied with what has happened. Right. So after the binary search tree, after the binary search tree, the next code, next topic is the Edelson, Welsky, and Landish tree. Edelson, Welsky, and Landish tree. So this Edelson, Welsky, and Landish, because the three scientists have designed this kind of a search. 3 scientists have designed this search. So, yes, Meghana. Yeah, yeah, Meghna. Let me know. A doubt is in BST. Yes, Meghana. Let me know your doubt. In order, left root, correct. How did you? It will come in the ascending order, isn't it? No, 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 no. Meghana, when phi is inserted, when phi is inserted, phi doesn't go to the right of 6. Are you getting my point? Because phi is less than 6. Where was the root? Root was 6. And phi goes to the right of 4. So first it goes to the 4. 4 of left is nothing. So 4 gets printed. Yeah. So when I inserted 6, 4 and 5, the order is going to be 4, 5, 6. Yeah. If it is 8, then it would have gone 4, 6, 8. Yeah, you are right. If 6 first, then 4, and then 8, then it would have gone 4, 6, 8. Yeah. That part is working okay. But only thing is that when the tree is not there, when the node is not there, that part in the demonstration is not coming correct. So if I, yes, student, hold the line. Students, hold the line. I'm coming. Okay, I'm sorry. There was small somebody at the door. Anyway, so if we run this code, we enter 1, we ask for 6, continue 1, choice 1, 4, we 1, choice 1 again, we enter 8, 1 again, and we display that is 4. So again 468. It should work like that. Okay, Meghana, that part is working quite okay. Only thing is that when there are no nodes, there is some problem which I will solve before I send the code to you. Okay, Meghana, are you left, root and right? Now again, if we enter 1 and go for 1 and say 5, 1 again and display 4, then 4, 5, 6. No issues. Okay, now is it clear? So this is how it's going to happen. Yeah. So continuing with the class. So AVL tree. That AVL name has come from three scientists who gave one more kind of a data structure, which is further improvement of your BST, that is binary search tree. They were Edison, Velsky, and Landish. These three scientists they created. So therefore, it is in a short form. It is termed as AVL tree. In a short form, it's termed as AVL tree. So let's before we actually go over there, we should know what is a balanced binary search tree. We know BST, but there is a small difference of a balanced binary search tree, right? A BST and a balanced binary search tree. Let's first try to understand what is the difference. Because AVL tree, the basis of the AVL tree is a balanced BST, right? So what is this balanced business, right? We know we have considered this that this is a root, this is a left subtree, and this is the right subtree. The left subtree has got two children. The right subtree has got the right child, which has got a left child, right? So the basics I would like to refresh. Your basics I would like to refresh. That when you look for the height, you start from the root and go to the longest kind of a uh, leaf, right? Or the leaf which is farthest. So if you come to this, the height at this is 1, the height at this is 2, and we are getting the height as 2 if I traverse this way or if I traverse this way, right? Then I also, to confirm the height, I also traverse to the right. The height is for this along this is 1, 2, and 3. So the since this is the longest, so therefore the height over here becomes 3, right? So height of the tree is the deepest kind of the leaf, okay? Whereas the depth of the root is 0, depth of the these siblings is 1, depth of these siblings is 2, right? Whereas the height of this tree is this side it is 2 and this side it is 3. So basis, with this basis, let's try to understand what is the difference between a balanced binary tree and a binary search tree. The height of the node is the number of edges on the longest path from the node to the leaf. This is the longest path. So from the node to the leaf, when I came, compared to this is the longest path. Therefore, we have taken the height as 3. Okay, so the of the height of the leaf, if you just consider the height of the leaf, because there is nothing below, there is nothing below, so height of this is 0. From this, the height is taken, it is 1. From this on the left side, the height is taken, it will be 2. But the height of the tree, what I have written over here is this. So I go to the right, the height of this is uh, here it is 2 because 1 and 2. The height of this is 1 because there is 1, but height of this is 0, right? Going downwards. But on this path, we are getting the highest number of nodes. So we term this height of the tree as 3, right? So the height of the leaf means downwards is 0. Okay. The height of the non-empty tree is the height of the root, right? What the height of the tree is the height of the non-empty tree, that is the root. So the height of the root is the longest leaf node, right? So that is the basis we know, right? Now, following are the conditions for the height. This balanced binary search tree is also called as in some book height balanced binary tree. So balanced binary tree or height balanced binary tree both are same, right? What are the conditions? Let's look for the conditions. Condition number 1, difference between the left and the right subtree for any node is not more than 1, right? Now this is your 0, 1, 2, and this is the leftmost is 2, and rightmost is how much? 3. So at the present, if you look at this, the difference between the left subtree and the right subtree is 2 minus 1, which is 3, which is 1. So if you go by only point number 1, it looks like it is a balanced binary search tree or it is a height balanced binary tree, right? At point number 1. But there is one more condition. What is that condition? The condition is that the left subtree is also balanced. Left subtree is also balanced. So let us see whether the left subtree is balanced or not. Now the left subtree is this, right? Now the height of this is 1 on the left hand side. The right subtree height is also 1, right? So either either the difference between this and this should be 0, or at the most it can be 1, like in this case. Presently it is 2 and this is 3. So 2 minus 1 is 1. So presently it may look like that the left subtree is a balanced subtree. The tree is also a balanced subtree. But there is one more condition. And what is that condition? The condition is that the right subtree is also balanced. Now if this was not there, if this was not there, if this was not there, is the right subtree balanced? Right? Is the right subtree balanced? When I come over here, there's no leaf, right? So the left one, is 0, whereas this is only 1 here, and this is 2. So if I do not have in this particular case, on the right hand side, the height is what? I'm only talking about this right subtree. The right subtree, here this is 0 and here it is 1 and 2. So 0 minus 2 goes to minus 2, right? 0 minus 2 goes to minus 2. So it's not balanced. To make it balanced, what we know we should do? We should turn it something like this and add at least one child. So the left one is having height as 1, the right is having height as 2, right? So 1 minus 2 is minus 1. 1 minus 2 is minus 1. So then it becomes either a balanced binary search tree or height balanced binary tree. Students, are you clear? because this is the basis of your AVL. This is the basis of your AVL. If you have not understood this, AVL is not understood. Yeah, yes, Raghavendra. See the previous case, right? In this situation, first is the difference between the left and right subtree cannot be more than 1. Okay. If I see the left subtree, the height is 2. If I see the right subtree, the height is 3. So height of the left subtree minus height of the right subtree compared to the root, I mean taking the root as the point, the left subtree height is 2, the right subtree height is 3. 2 minus 1, 2 minus 3 is minus 1. So it is balanced as per the definition. But there are two more points to make it balance. The When I come to the left subtree, the left subtree also should be a balanced subtree. Means what? Its left height and its right subtree, the difference should be either 0 or at the most 1. So here it is 1, here it is 1. So 1 minus 1 is 0. So this left subtree is balanced. Now let's come to the right subtree. The left height is 0, whereas the right height is 2. The right height is 2. So 0 minus 2 is minus 2. Right? Therefore, the right is not a balanced subtree. So at the present, it is not a balanced binary search tree. Students, are you understanding? Raghavendra, as you are seeing in the diagram, okay, Akashdeep, yeah, and others, place your point. Akashdeep, height of the right subtree is equal to the height of the left subtree. Height of the right subtree is greater than or equal to height of the left subtree. Yes, it can, but if it is like that, that for it to become a balanced binary search tree, the acceptable is that when you subtract the height of the left subtree minus the height of the right subtree, at the most I can accept either 1, minus 1 or 0. Then only it becomes a balanced binary search tree or height balanced binary tree. Akashdeep, am I with you? Have I understood what you are trying to say? Jolly, I'll come to you. Okay, Akashdeep, you are with me. Okay, yeah. Jolly is saying, sir, here the difference between will be minus 1 only. Which one you are talking? The present diagram? Aman, you are talking about the present diagram? Yes. Yeah. But see, to make it a balanced binary search tree, Aman, at the present, 2 minus 1 is minus 1, fine. But see the point number 2, the left subtree should be balanced. Which is the left subtree? This. Is it balanced, Aman? Only this left subtree. Is it balanced? Yes. Now let us come to the second point. That is the left subtree is balanced. The third point is the right subtree is also balanced. Now let's come to the right subtree. Is it balanced? What is the left subtree height? Aman. Left subtree. So the difference is 2. Since the difference is 2, condition 1 was getting satisfied. 2 minus 1, 2 minus 3 minus 1, true. Left subtree is balanced, 1 minus 1, 0, true. But the right subtree, which is the third condition, the right subtree is balanced. The right subtree was not balanced in the previous case, right? So if to make it balanced, if this is the place, that is, had I one left child, had I one left child over here, so the height is 1 and the height is 2. So 1 minus 2 is minus 1. Then it becomes balanced. Then the overall, the complete tree becomes the balanced binary search tree. Yes, Aman, are you with me? Aman and others. All right. All right. Good. So this other students, please participate if you are not understood. Always I find Aman, Raghavendra, Jayashankar, Rohan, Meghana, other Meghana, sir, 450 students. Some of the students are understanding. If you are not understanding, did I ever stop you? Don't ask questions, okay? Arey Baba, clarify your mind. I know there is a lot of pressure on you. 1-2 exam is there, 2-1 exam is there, your backlogs are there, that is, your supplementaries are there. Then there's a new method of learning, that is online teaching. You have to first get adopted to this. Please feel free to clarify the doubts. If you are not feeling free with me, on Thursday, there's a special class for you with your faculty, with a limited group of 60 students. Keep your doubt in your mind. So I assume that the balanced binary search tree is clear. Now coming to the AVL tree. The definition. The definition. AVL tree is another balanced binary search tree named after the inventor Edison, Velsky, and Landis. They were the first dynamically balanced tree to be proposed. Right? There are other balanced trees also, uh, red and black and splay, but they were the first one, so we are studying that. Okay. So see the definition. A AVL tree is another balanced binary tree. So first we should know what is balanced binary tree. So what is balanced binary tree? Balanced binary tree, search tree, right? BST, but balanced, right? BST is balanced. So the other examples are red, black, and splay. They are not perfectly balanced, but pair of subtree differ in the height by at most 1, right? So if you see the O notation, maintaining means insertion deletion becomes O of log n, right? So O of log n is your big O notation for your AVL tree. Now the AVL tree is a binary search tree which has the following properties. Firstly, it is a BST. BST means what? BST is a binary tree. In addition to being binary tree, the left tree key is always less than the root, and the right subtree, the keys are always greater than the root, right? So that is what is your binary search tree. But we are adding the factor of balanced, right? We are adding the factor of balanced. So AVL tree is a binary search tree which has got the following properties. Property number 1, the subtree of every node differ in height by at most 1. That is, the left's height minus the right height is either 0 or 1. Alternatively, just now you have seen when it came to minus 1, alternatively, LH, that is the height of the left tree, minus the height of the right tree, either could be minus 1, 0, or 1. Minus 1 means 2 minus 3 is minus 1, that way. So that time it is acceptable. 1 minus 1 is 0, that time it is acceptable, right? 2 minus 1 is 1, that is also acceptable, right? So 0, minus 1, 0, or 1. This is the mod of your left edge minus right edge. Mod of your left edge minus right edge. That is the condition number one. Every subtree is an avial tree. Like what Jolly was asking me, even every subtree has to be avial, right? In the previous example, when I displayed this, at this particular point, the tree was balanced, the left was balanced, but the right was not balanced. Therefore, it is failed to become an avial because every subtree, even this subtree, has to be avial. That's what every subtree has to be an avial tree. Then only it is balanced. Okay. Pictorially, we can represent this is the root, right? This is the height. This is the height. The difference of these two can be at the most 1. The difference of these two can be at the most 1. Either 1, 0 or minus 1. 1, 0 or minus 1. Now, is this avial? Now, any other student? I want some other students to participate. Oh, Saurabh has come. Saurabh, is it BST? You are saying it is yes. Is it BST? Binary search tree. Let me interact only with Saurabh. Let me interact with Saurabh. Yes, sir, it is BST. Saurabh, any 2 points why you are saying BST reference to the root? Saurabh, you are saying it is BST. Justify why you are saying it is BST. The values are less than 12 on left side of the tree. Correct. First point correct. And greater on the right. Correct. And every node has maximum 2 nodes. Yes. Now, to be an avial, what is the height of the left subtree, Saurabh? 3. Very good. What the height of the right subtree? 2. So 3 minus 2 is 1. Right? Now, that's when you are referring to 12. Right? Let's come, because the avial definition does not stop at 12. Let's see whether this subtree is avial. Right? First, is it BST? Yes. Why? Because the left nodes are less than the root and the right node is greater than the root. What the height of the left subtree? 2. What the height of the right subtree? 1. 2 minus 1 is 1. So the second point is also ticked right. Now let's come to the right. This is my right subtree. Is it in avial? What the height of left? 1. What the height of right? 0. 1 minus 0 is 1. Right? So it is perfectly suiting all the conditions which are required to declare it as your avial. So is it avial? Example shows that each left subtree, each right subtree. Therefore, it is a avial tree. Yes. Not less than or equal to. Less than or equal to could be Raghavendra. Less than could be true also. H1, H2, if the difference is 2, then it fails. The mod of H1 minus H2 could be minus 1, 0 or 1. Nothing that. So I cannot generalize less than or equal to 1. Less than 1 could be 0, it could be minus 1, it could be minus 2 also. If it is minus 2, we have a problem. We have a problem. Okay, Raghavendra? Okay, so to understand the AVL, definition further, let's take one more example. Before I go, students, let me syllabus. Let's stick to the syllabus. My primary responsibility is to complete the syllabus. Now, what I have underlined, we have finished in today's class. What I have underlined, we have finished in today's class. That is the binary search tree, the definition, implementation, operation in that searching, insertion, and deletion. We have completed. Now we are coming to AVL tree. Again, the definition we have finished, height we have finished, right? Operations, insertion, deletion, and search, right? That we are going to do. That we are going to do. Okay. So yeah, so I deviated from here. So this is an example of AVL tree. I'll take a couple of minutes, cover one more point, and then there is a quiz. I'll hand you over to Shankar sir. Insertion. As per the syllabus, insertion in the AVL tree is there, so we should understand. Implementation of AVL tree insertion rely on adding an extra attribute. Means the node. Yeah. What is this extra attribute? When you are inserting, what extra attribute you have to consider? Binary search tree, when we are inserting, we are just taking care that it is in the binary form, right? That is, if it is less than the key, you are coming to the left and inserting it over there, right? Yes, Rohan and Jolly are spot on it. The additional attribute which we should see, the addition, yes, Sahitya, you're also right. Height of the left and right nodes. The additional attribute which has come is what? What is the extra attribute? That extra attribute is the balance factor to each node. Adding correctly and making it BST is not sufficient, right? Adding as per the BST is not, or inserting as per the BST is not sufficient to make it AVL. When you insert, you are going to question, is the left subtree and right subtree difference is either -1, 0 or 1. If it is not, then we have to do some other job. So that is what is your extra attribute as far as your insertion or deletion in the AVL tree is concerned. Yeah, Bhuvan Sai Reddy. Yes. The Bhuvan Sai Reddy, the issue is that when you are trying to do the search insertion, deletion and searching operation faster compared to your BST. Therefore, this AVL concept has come. Therefore, the AVL concept has come. Okay. Right. So, what is the factor that indicates whether the tree is left heavy? Now, I'm saying when I say the tree is left heavy, when the tree is left heavy, Bhuvan Sai Reddy, are you okay with what I See, uh, the insertion, search, and deletion, as far as your BSc is concerned, is login, right? To improve the deletion, we want one more data structure, one more data structure, so that this AVL is going to help in that manner. Therefore, that balancing factor. By balancing, I'll give you an example. I'll give you an example. Keep the doubt at the back of your mind. Once I take one example, I think it will be clear. So, since he's asking me, I'll come back to right. See, we are saying this is not an AVL. Why? The left height is how much? 1, 2, 3. The right height is how much? 1, 2, 3. 3 minus 3 is 0. But are we stopping at that? No. Again, we are coming over here. What the left subtree? 1, 2. What the right subtree height? 1, 2. 2 minus 2, 0. Fine. So far, good. What is the left height? 0. What the right height? 2. 0 minus 2. Minus 2. False. Yes. So it is not in the AVL format. Right? So if this AVL concept is not there, Bhuvan Sai Reddy, 25 no. What are you saying, Aman? Any point at note 25? What's your point, Aman? 25 note? Not balanced. Not balanced. Yes, I'm also saying the same thing. That 25 node is this subtree is not balanced because left is 0 and right is 2. Yeah. Burns I ready. So you agree that this is so simply inserting. If AVL concept was not known, I got 30 first, I inserted here. I got 27 next, I inserted here. Right? This is one way of data structure. One way of data structure. But an improvised way of data structure so that my insert, search, and delete operation is further improved. For that purpose, we go to a balanced binary search tree. And since this concept was first given by the three scientists, therefore it is called as AVL. Yeah. So how it is going to improve? Yeah, that's what. See, the the depth the depth being limited, and if the depth is not limited, we are going to reorient the entire tree to make it limited. That's why. Let's take one example, right? Presently, presently, we actually want to insert 14, 15, and 16, right? So my root is say 14. First insert 14 and 15. My root is at 14, right? And the one more node is 15. Is it in the AVL format? Yes. Why? Because the left is 0 and the right is 1. So 0 minus 1 is minus 1. Now let me insert 16. So presently 0 minus 1 is minus 1. Fine. Now let me, therefore it is balanced. So now if I insert 16, now when I insert 16, what's going to happen? Since 16 is greater than 14, I'm going to come here, right? So as far as BST is concerned, I'm correct. But as far as AVL is concerned, I'm not correct. Why? Now suppose if I have to search 16 Aman, there are two nodes, so n is 2, right? If I do this rotation, if I do this rotation, how? How do I do this rotation? The rotation is done around this. By rotating this, what happens? 15 becomes the root, right? So since 15 has become the root, if I had to search 14, I have to go only one. If I had to search 16, I have to go only one. In the previous case, when 14 was the root, I had to go two depths. Now I have to go only one depth. I have to go only one depth. That is how I am performing the search operation faster. Jolly, am I clear? Okay. So this is how the insertion activity happens. When you insert in the BST, in the previous case, it was fine. As far as BST is concerned, 16 was inserted. But it is not in the AVL form. To make it in the AVL form, I have to balance it. How do I balance? Instead of 14 being the root, I change the root as 15, bring 14 to the left and bring 16 to the right and bring it in the AVL form. Okay. I'm stopping now and handing it over to Shankar sir, who is having a quiz for you. Please do not log out, attempt the quiz, and then only leave. True, AVL is more efficient than BST. True. Yes, Bhuvan Sai Reddy.